We're going to talk about potential energy and the effects with intramolecular forces. Now, obviously, we're going to talk about molecular compounds and ionic compounds, and I hope you remember that molecular are covalent bonds with two or more nonmetals, and ionic is a nonmetal bonded to uh, metal, and they transfer electrons. Okay, so I'm going to gloss over some of this because you're very familiar with it. Um, Obviously, if you notice that delta H is positive, that tells you that it's an endothermic reaction. And I don't know if you remember when we were looking at the hand warmer activity, we were looking at what happens to temperature. And when you dissolve something like sodium chloride, it actually takes in energy because it requires energy to separate the I'm sorry, not to separate, but to have the separated ions be attracted to the water. So that's why we have an endothermic reaction. And notice that, although I wouldn't say that's a reaction, I'd say dissolution. Notice that ionic bonds tend to be very strong because they have a attractive force. And our good old friend Coulombic force of attraction. So, with the Coulombic force of attraction, we're talking about the positive and negative ions. And the closer they are together, the stronger the attraction. Okay, so here we're looking at melting point of solids. And notice they're all ionic. So we have a metal with a nonmetal. But the question is, what is the difference? Now, if you look at fluorine versus iodine, hopefully you can remember which one is the bigger ion. And when you look at that, it shows that fluorine is smaller, therefore the attraction should be higher because the distance between lithium and fluorine is smaller, therefore the attraction is higher. So the melting point should be higher for lithium fluoride. Now here we have two ions versus one. So the question is, which one's going to be the higher melting point? So because magnesium oxide has a greater charge, that is what affects the melting point. So in this situation, we're not talking about the number of ions, we're talking about the charge of the ions. And oxygen has a -2 charge, so as a result has a greater melting point. And then once again, we've got size of metal. So we have sodium and we have magnesium. And the question is, which one's going to give you a greater melting point? So notice that magnesium iodide has a higher melting point. This situation, it's not necessarily size, but charge. So magnesium has a +2 charge. As a result of it, it has a higher melting point. Okay, so AP likes to give pictures in their free responses. So you have to decide which one would have a higher melting point and why. So notice that you have metal with a nonmetal that are different charges for letter A, and then for B, it looks like they're similar charges. So notice that B has a higher melting point because it has similar charges. And notice that the metal has a smaller radius, but together B gives you a higher melting point. Okay, now we're going to talk about bond energy, and some of this is review. We've talked about it when we were looking at thermodynamics. So please remember that when you're talking about distance between substances or ions or nuclei, the further they are away, the higher the potential energy. But the closer together they are, the lower the potential energy. Now, notice that energy is released when you form a bond, and that's because you're essentially bringing two atoms together, and as a result of it, they release energy. Obviously, when we're looking at breaking bonds, also we have to put in energy because we're increasing the distance between the two original nuclei. Okay, so notice that the amount of energy required to break a bond should be the amount of energy that is released depending on what you're doing with that bond. Okay, so here is an example of a reversible reaction. So we have hydrochloric acid, and when you break the bond, it's endothermic. Notice that when you form the bond, it's exothermic. Now, this slide should look familiar. It was one of your free response practice questions, and they were comparing oxygen with nitrogen. Here is just hydrogen. And notice that as you bring hydrogen closer together at the bottom of this curve here, the energy obviously becomes more negative. Now, if you're going back up this curve, it's going to become more positive energy or require. So here is where they release the energy. Now, I don't know if you remember, but nitrogen had a curve on the left and oxygen was a curve on the right, and that's because of internuclear distance. So notice with hydrogen, its internuclear distance is 0.074, okay? So bond length will determine where the base of that curve is. So notice that potential energy will decrease as you bring the atoms or the nuclei closer together, okay? So notice that 0.074 nanometers, that is where energy is at its lowest point. Now, obviously, if you move to the left, potential energy rises, and that's why it becomes more positive. Okay, so the other thing that is important to remember is that when bond length increases, bond energy decreases. So it's important for you to be careful with how you represent things or the way you relate things together. So obviously, the closer two nuclei are to each other, the stronger the force of attraction. So if you have a longer bond, you're going to have a lower force of attraction. Here is an example of 3 compounds. And notice that when we're talking about iodine, we're talking about a larger bond length. And as a result of it, the bond energy is lower. So notice that when we're talking about chlorine, when we look at bond length, the bond length is shorter. As a result of it, the bond energy goes up. So please, please, please remember, the closer the nuclei are to each other, the higher the bond energy. Okay, so here is an example where we're just looking at a space-filling model here. And notice that the first compound, they're the same size, whereas the second compound, they are not the same size. So they want to know which had the least amount of potential energy and which one has the lowest bond energy. Oops, sorry guys. So notice that number 1 has the lowest bond energy because it has the shortest bond length. And number 2 has the lowest bond energy because it has the longest bond length. Okay, so here we're talking about the difference between single versus double versus triple. Okay, now please remember that if you're increasing the amount of electrons between 2 atoms, you're increasing the attractive forces. So as a result of it, you're essentially pulling those 2 atoms closer. So notice with the first example here, we have a single bond, they're further apart. Double bond, they're slightly closer. And then triple bond, they're the closest. Therefore, this is going to require the most bond energy since it's so close. So as a result of it, when we have a triple bond, notice that its distance is 0.110 nanometers, and as a result of it, its bond energy is 941. The opposite is a single bond where it's 0.144 nanometers, and as a result of it, its bond energy is not as high. So if you increase the number of bonds, you're increasing the bond energy. Okay, so bond order is kind of a way that we can describe what's going on with the bonds. The only thing you really have to worry about is the fact that if you have a single bond, it's a bond order of 1. If you have a double bond, it's a bond order of 2. If you have a triple bond, it's a bond order of 3. And notice that when they're talking about bond order, the higher the bond order, the shorter the bond is, um, and bond energy increases. Okay, so here are some examples here where they have number 1 is a triple bond, number 2 is a double bond, and they want to know which one has the lowest potential energy, and then they want to know which one has the lowest bond energy. So notice that for number Roman numeral 1, because it's a triple bond, it has the lowest potential energy because those two atoms are the closest. Therefore, Roman numeral 2 has the lowest bond energy because instead of a triple bond, it's only a bond order of 2. Okay, so the difference between space filling and ball and stick model, notice that space filling doesn't show exactly where the 3D positions of the atoms are, whereas ball and stick shows where the position of the atoms are. Ball and stick is good at representing single, double, or triple bonds, but space filling will show the relative bond length. Ball and stick, the size of the atom is not proportional, whereas space filling, it does show the proportion. And then sticks are not proportional to bond length, but space filling does show the number of bonds between the atoms. Okay,